Okay, in this video, we're going to take a look at phase change diagrams. Phase change diagrams take into account temperature and pressure and how they cause phase changes. You may know that phase changes occur if you heat or cool a substance, but you should also realize that phase changes occur if you change the pressure of a substance. That can also make a phase change happen. What we can do with one of these graphs is, well, their basic setup first off, is that temperature generally is on the x-axis, and here it is, in degrees Celsius, and pressure is on the y-axis. Here's pressure in atmospheres of pressure. Just to give you some perspective, Earth's atmospheric pressure at sea level is 1 atmosphere of pressure. The average temperature on our planet is somewhere around 20 degrees Celsius. Room temperature is 23 degrees Celsius. Now, the graph is divided into zones. We have solid, liquid, and gas, or vapor, on this one. And those are the 3 phases of matter. Likewise, the boundary lines between solid and liquid, between liquid and gas, and between solid and gas, those represent phase change points. So this line between solid and vapor, that represents sublimation and deposition. So any temperature and pressure that's along this line will be a set of conditions at which the substance will sublimate or deposit from gas to solid. Likewise, our line between solid and liquid, that's our melting and freezing line. And our line between liquid and gas, liquid and vapor, that's our evaporation condensation line. And again, any set of temperature and pressures that fall along one of those lines, those are conditions where you'll have a phase change. Now, if you plot conditions, let's say you look at 0 degrees Celsius and 1 atmosphere of pressure, which is right where the marker is here, that falls within the gas zone of this graph. So that means that carbon dioxide at 1 atmosphere of pressure and 0 degrees Celsius, which is 32 Fahrenheit, carbon dioxide would be a gas in those conditions. So you can do that for any temperature and pressure on the graph. Another thing to keep in mind is that each substance has its own unique phase change diagram. This one is for carbon dioxide. We'll take a look at waters in just a minute. Now the trends, our temperature trend, generally as the temperature or as the kinetic energy increases, our phases will transition from solid to liquid to gas. And you see that here. As temperature increases, our solid is mostly here on the lower temperature side, and then we get into liquid at warmer temperatures, and then finally we have gas over here at the higher temperatures. So as temperature increases, we go from solid to liquid to gas. As temperature decreases, we would go from gas to liquid to solid. Now, the pressure trend, what if you change pressure? Well, as you increase pressure, the trend is that we go from gas to liquid, finally transitioning into solid. So if we look here at 0 degrees Celsius again, so initially at lower pressures, our CO2 is a gas. If we increase the pressure with the temperature remaining at 0 degrees Celsius, eventually at probably about 50 or 60 atmospheres of pressure, our CO2 will transition into a gas. If we continue increasing the pressure at 0 degrees Celsius and follow the marker here, eventually we will solidify, we will freeze the carbon dioxide. That would be at an extremely high pressure. So as we increase the pressure, the particles are shoved closer together and they transition from gas to liquid to solid. Some other things we see on the graph, another special place, is what's called the triple point. This is a set of conditions in which all 3 phases of matter coexist. For carbon dioxide, it's at about 58 degrees below 0 Celsius and at about 7 atmospheres of pressure. And what happens in those conditions is that we get a dynamic equilibrium. And that's a set of conditions where We have freezing, melting, condensation, evaporation, sublimation, and deposition all happening at once. So in reality, all the phase changes are occurring, but there's no net change, no overall change. So that's the triple point. Again, it's a pressure and a temperature where we'll have all three phases of matter. The other thing that's marked on a phase diagram, phase change diagram, is what's called the critical point. And often when you look at these, and you can see it here, this is the phase diagram for water, the line between liquid and gas, our evaporation condensation line, eventually it just stops, and it's marked with a point. That point where the line stops between liquid and gas, that's called the critical point. And this is a temperature where if you get past that temperature, you cannot compress the gas into a liquid. So here with carbon dioxide, if we get above about 35 degrees Celsius, even if we have a gas, we will not be able to compress it into a liquid. And we call those supercritical fluids. Supercritical fluids are gases that are past their critical point, and so they act kind of like a gas and kind of like a liquid. They're often used as solvents in industry because they're really good at dissolving things that are hard to dissolve. But the critical point, it's a temperature past which the gas can't be compressed, and if you have something that should be a liquid, but you're past that critical temperature, it also acts like a gas. Those are supercritical fluids. So phase diagrams, phase change diagrams. Again, here's the diagram for water. So water's triple point, just above 0 degrees Celsius, 0.01 degrees Celsius, and a very, very low pressure, 6/1000ths of an atmosphere, which happens to be the average atmospheric pressure on the planet Mars on most days. Just a little factoid there. But that's water's triple point, low pressure, just above freezing. Water's critical point is at 374 degrees Celsius, 218 atmospheres of pressure. That's 218 times average atmospheric pressure at sea level on planet Earth. So water's phase diagram is a little bit different because water is a different substance than carbon dioxide. And again, every substance will have its own phase change diagram. Okay, try some practice problems, review your notes, do your best. Thanks, everybody.